Hey crew, here we are again. These are our 8.5 notes on compound interest. So the idea of compound interest is an application of our exponential growth functions where the interest rate is, the annual interest rate is added in a portion of the annual interest rate is added several times a year instead of just knowing what interest we get over the course of the year. So the formula we're going to use is this formula here, where the B stands for the balance, which is the amount of money that's in the account at any particular time. P, which could be for principal, is our initial deposit, so that's here where we would have A in our Y equals A times B to the X formula. The annual interest rate, our R, is put up here, and it's as the numerator of a fraction because N, the number of compounding periods per year, is what we're going to divide that rate by, and we're going to add it that many times per year. So we'll see that in an example. T would be the number of years that the account accrues in the interest. So this is similar to our general form, right? Particularly if we replace our B with that 1 plus R and the X with a T. The difference is that we're not just looking at what we end up overall as a percentage at the end of a time period at the end of the year, but we're adding a portion of that percentage multiple times throughout the year. All right, let's look at an example. So try to keep this in the picture here. All right, so let's suppose that we have $1,000 that's deposited into our account. So this is our principal. And that account is going to pay 6% annual interest. So that gives us our R value as a decimal, which is 0.06. That interest is compounded or calculated and added monthly, which makes our N equal to 12. And the question is, how much money, right? How much money is in the account? So that's asking us to find the balance after 1 year. So that would be when T is 1, or after 15 years, that would be when T is 15. So we're going to start finding the balance after 1 year. And we're going to follow the format of this equation here, and we'll fill in what we know. So we have our P, which is our initial deposit, and that is $1,000. We're going to multiply that by 1 plus our interest rate. Our annual interest rate is 6% per year, but we're going to calculate a portion of that 6% every month. And since there are 12 months in a year, we're going to add a 12th of that 6% interest, and we're going to do that every month. So our exponent is going to be for the number of months in a year, which is 12, times those number of years, which in this case is 1. So if we evaluate that with the help of our calculator, we end up with $1,061.68, right? So 6% of $1,000 is $60, and you can see here that we end up with a little bit more than $60 because adding a 12th of that 6% interest is calculating a percentage of a larger and larger amount over the course of the year, right? Instead of just gaining a strict 6% during that year. Okay, let's look at what happens after 15 years. So if we find the balance after 15 years, we've got our $1,000 initial deposit. We're going to multiply that by 1 plus 0.06. We're still compounding monthly, so we'll divide that interest by 12, and then we're going to add, calculate and add that interest 12 months a year for 15 years, right? So we would make sure that all of this gets multiplied together and put into our exponent, put that in our calculator, and we end up with $2,454.09. So over the course of 15 years, right, our initial deposit, $1,000, grows by almost 2.5 times. So that brings us to our next little discussion, which is on nominal versus effective rate. So the nominal interest rate, right, that nominal comes from the word that means name, is our named rate. So this is, right, our advertised annual percentage rate. Because like in situations up here where we actually ended up with more than 6% when that rate was 6%, we have what is called the effective rate, which is the actual percent, right, of the initial, right, that is added over the year. So it's the percent more that we end up with at the end. Okay, that's our effective or effectual year. So you can read through this discussion, which kind of reiterates what I said. Let's look at how to use this. So in this first example, if we take $1 and we grow that dollar by 6%, this is our R value, and we compound that 12 times a year, this is our N value, then that dollar becomes, when we work this out, 1.06168. 6% of $1 is 6 cents, and you can see that what we've added is actually a little bit more than 6 cents. So if we come down here, our nominal interest rate is the 0.06, which is 6%. But effectually, in the end, we actually added 6 cents plus a little bit more. And that effective interest rate, which we're going to call EIR, right, comes from what's going on here. So that will equal, right, what 1 plus R is divided by N raised to the N. So what we end up with at the end of one time period minus what the initial investment would be, which would be 1. So if we apply that here, right, this quantity is this 1.0618. We subtract 1 and we end up with 0.06168, which is a percent is 6.168%. So our nominal rate is 6%, but effectually we actually end up with 6.168% at the end of a year. All right, now let's look at what happens when we have interest not just compounded once a year, or once a month, or once a day, or even once a second, but we compound that continuously, right? And we already know this formula that the balance will equal the principal, the initial deposit, times e to the RT. So here we're just using R instead of K, but that is still, right, the annual continuous interest rate. So in this case, our nominal interest rate is our R, and our effective interest rate is not this, but is e to the R minus 1. Okay. So if we apply that in an example, right, this is asking us to find what is the effective annual rate, so what is my EIR, for an account that pays interest at the nominal rate of 6%. So that gives me my R is 0.06, right, when it is compounded daily. So that would be N equals 365. So my EIR for daily will equal 1 plus 0.06 divided by 365 to the 365 minus 1. I evaluate that and I end up with I end up with 0.06183. So that is an effective interest rate of 6.183%. Okay, Okay, now, what if I were to compound hourly? Well, if I compound hourly, then that changes my n to the number of hours there are in a year. So that's going to be 24 hours a day times 365 days a year, which gives me 8,760. So my effective interest rate, if we compound hourly, will be 1 plus 0.06 divided by our 8,760 raised to the 8,760, right? And then we're going to subtract the 1. So we work that out and we get 0.061836, which is 6.1836%. I think that here, this was actually a 1. So you can see these are actually very close. They differ only in this place. So continuously we do get more overall in the end, but not that much more, just a little bit more. Okay, so last example, we'll pull in the idea of continuous here. We have the question, which is better, right? Which is better? An account that pays 8% annual interest rate compounded quarterly. So in this we get R equals 0.08 and N equals quarterly. That would be 4 times a year. Or an account that pays 7.9% interest compounded continuously. So in this we would get that R, right, or K, if we want that form, is 0.0795 and it's compounded continuously. So we've got that continuously. So when we ask the question, which is better, what we're really looking for is what is that effective interest rate? So let's look at that. Our effective interest rate for the quarterly compounding will equal our 1 plus 0.08 quarterly. We would divide by 4 and raise to the 4 minus 1. So we evaluate that and we get 0.08243, which is 8.243%. That's our effective rate. So at the end of the year, we would earn back 8.243% of what our initial investment was. If we look at our EIR for our continuous growth, we get what E to the R is, so that would be E to the 0.0795. Right? That would be our equivalent growth factor, so that would be like our B. And then we would subtract 1 from that, which gives us our R. So that's consistent with what we've learned in the past. So that's 0.08275, which is 8.275%. So we come in here and we want to know which is better, so we compare these two. And the one that's better is the one that has the larger effective rate, and the 8.275 is larger. And so our conclusion is that the 7.95%, right, compounded continuously is better. So actually a slightly lower interest rate than the 8%, but the continuous compounding gives us actually better return on our money. Okay, so those are our last ideas for this unit. Work on those and we'll talk more about it